The mean value theorem for integrals. It says that there's got to be a location C in between A and B so that its height is magical. Call it f of C. Here's a little sketch. Call it f of C. See, that's the height for C. What's magical about it? The height is so perfect that the area of this rectangle is exactly the same as the area under the curve from A to B. And you can see why that makes sense, because the area that this rectangle takes care of here would compensate for the area that it missed over there. So that's what the mean value theorem for integrals says. It's saying that the true area under the curve equals the height of this rectangle times the base of the rectangle. F of C is the height, B minus A is the base, the width, however you want to say it. So pause this and write that down. Now, if we divide both sides of this equation by B minus A, we would be left with F of C, which is that magical height that makes this perfect rectangle, where the area of this rectangle would be the same as the area under f of x from A to B. So the mean value theorem for integrals is talking about the existence of this C value, which is an x value. But the math work you're going to do today focuses on finding the average value, f of C. Let me turn the page. If you divide by B minus A, you're going to get 1 over B minus A on this other side, and we would set this equal to f of C. Here's another picture showing that average value, that special height. So f of C, this is the average value for the function f of x. F of C is the average value for the function f of x. So your homework problems are still going to be just definite integrals. The only difference is you're going to multiply by 1 over B minus A on the front. Example. Get this to focus here. Find the average value of 3x squared minus 2x on the interval from 1 to 4. Well, you're just taking the integral from 1 to 4 of this function, but you're also going to multiply by 1/3. So there's the antiderivative from 1 to 4. Here's that 1/3, and just make sure you multiply it by 1/3 at the end. Very little new math today. The average value would be like when we had the jet fuel problem, and we figured out the average rate of fuel consumption by multiplying by 1 over 90. The other thing we've got today is the second fundamental theorem of calculus. Your book calls it part 1 of the fundamental theorem of calculus. We'll always refer to it as the second fundamental theorem of calculus. And it is to find the derivative of the integral, which you could probably guess would get you back to what you need to have. There's 2 ways we can write that notation. Either the derivative of the integral of something, or capital F prime of x. Both notations would represent the derivative of the integral. And this is showing that all you do is take the x and you substitute it in for the t. What it doesn't show is that you also have to multiply by the derivative of the upper limit right here. Here's an example right here. What's the derivative of the integral of cosine of t dt from 0 to x? You just take the x and you plug it in for the t, and you multiply by the derivative of x, which is 1. Well, that times 1 is just cosine of x. Here's another example where if you want the derivative of the integral, you just take the x and you put it in for the t, and so you get x squared plus 1 under the square root, instead of t squared plus 1 under the square root. Here we're going to take the x cubed and put in for t, and then we need to multiply by the derivative of x cubed. Something I should have pointed out but didn't is that the lower limit must be a constant. Doesn't matter what constant it is, it just needs to be a constant. That's why over here it said a and not x. Okay, we're going to skip a lot of what this book happens to show. We're going to go straight to, okay, here's what we're interested in. We need to take the x cubed and put it in for t. Skip all that u business. Just go right down to the very bottom. Cosine of t, nope. Cosine of x cubed, just like we said we were going to do. And then, what's the derivative of x cubed? It's 3x squared. And that's it. That's the answer. How can we double check our work? Well, we could actually take the antiderivative of cosine t, do a definite integral, so you're plugging in your numbers, then take the derivative of the answer. Well, let's show that this truly works. So what they did here is they took the definite integral here, get sine of t from pi over 2 to x cubed. So they plug in the x cubed, they plug in the pi over 2, they subtract. Sine of pi over 2, that's like sine of 90 degrees, that's 1. So you have sine of x cubed minus 1. Now that's the integral. If we want the derivative of the integral, we would have to take the derivative of this now. Well, the derivative of 1 is 0, so that's just gone. And the derivative of sine x cubed would be cosine x cubed times, chain rule, 3x squared, which they have down here. That's exactly what we got here. So the whole point of using this theorem is that you don't have to actually take an integral and then a derivative. If you want the derivative of an integral, you just, I'll recap it one more time, you take the upper limit, you plug it in anywhere there's a t down here. There could be multiple t's, so anywhere there's a t, you plug it in, and then you multiply by the derivative of that upper limit that you just used. That's it.